In August 2019, a camouflaged electric sedan performed 26 consecutive full-power launches, with almost no drop in performance. Any electric car could do one. Almost none could do 26. The secret wasn't the battery or the motors. It was a shoebox-sized device switching thousands of amps, 10,000 times a second. This is the insane engineering of the inverter. Every electric car is built around a contradiction. Its battery produces only direct current, but its motor is useless without alternating current. To understand why, we need to look inside. The motor's copper windings are split into 3 sets, each fed a sine wave offset by 120 degrees. Together, they create a smoothly rotating magnetic field, dragging the rotor along with it. Spin the field faster, and the car accelerates. Reverse the energy flow, and the motor becomes a generator, recharging the battery when you brake. The same hardware running backward. But the battery offers only a flat, unchanging wall of DC voltage. The inverter's job is to sculpt 3 perfect sine waves from it. And the way it does that is, at first glance, ridiculous. It cheats. By flicking switches on and off 10,000 times per second and varying how long each pulse lasts, its output averages into a sine wave. The motor smooths out the rest. But every switch transition wastes energy as heat, multiply by hundreds of amps, and silicon transistors bleed kilowatts. Heat is the villain of this story, and by the mid-2010s, it was a wall. The escape came from an unlikely material, silicon carbide. For a century, we used it to grind metal, but grown as a perfect crystal, it becomes a semiconductor with nearly triple silicon's band gap. That one number cascades, 10 times the breakdown field, far faster switching, far less heat. In 2017, Tesla bet the Model 3 on it, the first mass-market car with a silicon carbide inverter. The payoff: efficiency near 99%, and extra range from the same battery. When batteries cost over $100 per kilowatt hour, a better inverter is effectively free battery. And silicon carbide unlocked something bigger. Power equals voltage times current, and heat grows with the square of current. Double the voltage, and the same power flows with a quarter of the heating. That's why Porsche built the Taycan as the world's first 800-volt production car, and why it could launch 26 times in a row. It simply generates far less heat to begin with. 800 volts means thinner cables, kilograms less copper, and charging at 350 kilowatts, adding a kilometer of range roughly every 4 seconds. Hyundai brought it to the affordable Ioniq 5. So why did the industry wait so long? Because at 800 volts, ordinary silicon transistors fall apart. Silicon carbide and high voltage arrived as a package deal, and the package is spreading. There's just one problem. Silicon carbide is one of the hardest materials humans have ever tried to manufacture. It cannot be melted and pulled into flawless ingots like ordinary silicon. Instead, it's grown by sublimation in sealed graphite furnaces at 2400 degrees Celsius, atom by atom, a fraction of a millimeter per hour, where any drift seeds fatal defects. The result? Wafers costing many times their silicon equivalent, and a supply chain that became geopolitics. America and Europe poured billions into new fabs. The battery gets the headlines, the motor gets the spec sheet, but the quiet box between them decides how far the car goes, how fast it charges, and what it costs. So the next time an electric car pulls silently away from you, remember, somewhere inside it, a crystal we once used to grind metal is performing one of the fastest magic tricks in engineering.